So in this project, we will analyze the Amazon Electronic Reviews dataset from the 2023. And here's our content of our today presentation. And so in this dataset, it contains some rich information, including the review text, star ratings, helpful votes, and some product metadata. And our project goal is we wanted to explore three code prediction tasks. So first is the sentiment classification, where we determine whether a review is positive or negative. And second is the rating regression, where we predict the reviewers' ratings from 1 to 5 stars. And the last is the category classification, where we infer the product's main category from the review content. And our motivation is to understand how users describe their products, how textual cues relates to the rating, and whether we can identify the product categories purely from what customers write. And these tasks help us to showcase how multi-task modeling can extract both emotional and factual signals from large-scale review data. And here's our dataset and exploration. In the first slide, our first observation is that the electronics metadata activate a highly imbalanced category distribution. The all electronics and computers dominate the dataset, while many other categories like musical instrument or sport and outdoors appear only a few. So this long tail structure means that some categories have 10,000 of products, whereas others have only a few hundred. The overlaps among the product types, for example, phones appearing on both cell phones and Amazon devices, creates additional ambiguity. This imbalance makes the category prediction tasks particularly challenging because models must learn from a small amount of data in many subclasses. And second is the star rating distribution extremely skewed, with 5-star reviews dominating the dataset. Very few reviews fall in the 1 to 2-star range, reflecting the Amazon's well-known positively bias. This imbalance affects both sentiment and rating tasks. Sentiment classification must detect the real negative example, and RMSE for regression may appear lower than expected because most prediction cluster near 5-star. Methodless sampling or weighting could help mitigate these effects. And the last is the review length distribution. And we found a strong right skew distribution. Most reviews are extremely short, while a few very long reviews form a long tail. Um, this indicates that many samples contain limited textual information, which may weaken the model's ability to learn the meaningful signals. In contrast, longer reviews tend to contain richer cues that correlate more strongly with sentiment or ratings. So short reviews require more processing to reduce noise, such as we should remove the generic words like good or nice.
So now let's direct to our prediction model. The first prediction task is sentiment classification. The main goal of sentiment classification is classify each reviews as positive or negative. Before modeling, we first drop rows with missing ratings or empty review tags to clean the data. And then step 2, for each Amazon electronic review, we converted the 1 to 5-star ratings into a binary label. 1 equals positive and 0 equals negative. Step 3, to evaluate performance properly, we use an 80-20 trend test split with stratification on the label. Step 4, our baseline is the majority class classifier, which always predicted the majority. Although the accuracy of it is already about 80%, this baseline model doesn't rate the text at all and never catches any negative review. So it's really necessary to improve recall for the negative class. Next slide, please. Then step 5. In order to proceed the sentiment classification task, we apply TF-IDF vectorization to turn raw text into something a model can use. And each review is represented as a high-dimensional sparse vector of word and phrase weights. We include both unigram and bigram so the model can learn patterns like not working or highly recommend, which are very sentiment specific. We also cap the vocabulary at 50,000 features and remove common stop words to keep the model efficient while focusing on more informative terms. And step 6, we choose a linear model logistic regression while it scales well to hundreds of thousands of sparse TF-IDF features and gave interpretable coefficients for each word. And because the clauses are imbalanced, as mentioned before, we enable clause weight equals balanced, so the model penalizes mistakes on the majority clause more heavily and doesn't just mimic the majority baseline. And lastly, the accuracy improved by almost 9%. Next slide, please. The second prediction task is rating prediction. The main goal of rating prediction is predict the 1 to 5-star ratings for each review. For data selection and features part, after restricting the data set to reviews that have both a rating and non-empty text, in step 2, we pick 2 simple numeric features, price and number of helpful rows. For this step, missing prices are filled with the median price, which is robust to extreme values, and helpful rows defaulted to 0. Step 3, we also made an 80-20 trend test split for this task. Step 4, as a sanity check, we start with a very simple baseline, which always predict the average rating from the training set and completely ignore the tax and price. And the MSE of the baseline is around 1.6, while our MSE is about 1.27. Next slide, please. For generating the improved model, we also first apply TF-IDF as what we did for sentiment classification. And then step 6, after building the baseline text-only model, we noticed that TF-IDF captures review meaning, but it ignores important product level information. For example, price often influences how customers rate a product, like very cheap items tend to receive a more extreme ratings. And similarly, the number of helpful vote review gets can reflect how reliable the review is. So to incorporate this additional signal, we added 2 numeric features, price and helpful vote. However, this value operates on very different scales compared to TF-IDF features. So we applied standard scalar to normalize them, and then a column transformer allowed us to combine both text-based TF-IDF vectors and scaled numeric values into a single model input. Once we combine text and numeric features, our feature space grows extremely large, especially because TF-IDF generates a large amount of sparse mentions. We're trying to use ordinary linear regression here, but it overfitted badly and produced unstable coefficients due to the high dimensionality. Then to solve this, in step 7, we use ridge regression, which adds an L2 penalty to the loss function, and this penalty discourages large coefficients and stabilizes the model from overfitting. We set the regularization strength alpha to 1.0, which provides a good balance, which means it's strong enough to reduce noise, but still not that strong to suppress useful signals. And as a result, as we can see, the data at the bottom of the slide, both the MSE and RMSE of the TF-IDF plus numeric plus ridge model significantly outperforms the baseline. Next slide, please. The loss prediction task is category classification. In this task, we move from sentiment and rating prediction to a multi-class problem, predicting the product category directly from the review test. The metadata doesn't give a single flat label, it gives a category path. So we define the label as the leaf category, which is just the last element in that path. Then after apply last step to metadata in step 3, we join these labels to each review using parent ASIN. So every review now have a leaf category like earbud headphones or powder strips. And then step 4, we filter out empty reviews and then look at the category distribution. there are many long-tail categories with very few samples, which are noisy and hard to learn. And to keep the problem manifold and trainable, we restricted the task to the top 20 most frequent categories with about 69,000 labeled reviews returned. Step 5. Before training the real model, we used a majority class classifier baseline model as what we use for the Sentiment-1, which returns a 19.6% accuracy. Next slide, please. For the improved model, we only use the review text as input. We combine the review title and body and then feed them into a TF-IDF vectorizer. And same as before, we follow up of 50,000 features and include both unigram and bigram, which let the model pick up patterns that are diagnostic of certain categories. For the final step, on top of TF-IDF, we utilize a multi-class logistic regression model, which could not only minimize cross entropy over the 20 categories, but also gives interpretable widths that show which word are most associated with each category. And as a result, the logistic regression plus TF-IDF accuracy shown on the slide is dramatically improved. Next slide, please.
So I will be going through the evaluation. So for the first one, the sentiment classification with an absolute gain of the precision positive 9%. This demonstrates that emotional language such as excellent, highly recommend, or great values strongly influences the prediction. And on the right side, the confusion matrix shows the negative reviews remain harder to classify due to their scarcity and shorter text. So overall, the sentiment prediction is the easiest task because customers' emotion are highly expressed in the text. And second, for the rating prediction, the baseline model predicts only the global mean rating and achieved an RMSE of 1.26. So using the TF-IDF feature and linear regression, the RMSE dropped to the 0.94, 25% reduction in error. So the residue distribution centers around zero, indicating the non-systematic bias and a stable model across the rating spectrum. So that slightly heavier taste, suggesting that the extremely positive or negative reviews and ambiguous content are harder to model using text alone. Incorporating the metadata such as price, brand, or product features could further improve the accuracy. And lastly, the category classification is the most difficult task due to the extreme class imbalance and the overlapping vocabulary across the electronic subcategory. So the baseline achieved only 0.1956 accuracy, and for our improved model, the increased accuracy to 0.69, a dramatic for 9.6% improvement and more than 3.5 times better than the baseline. However, so many reviews never explicitly mention the product type, and products often belong to multiple hierarchical categories, limiting what can be inferred from text alone. So those results suggest that category prediction will greatly benefit from incorporating the structured metadata.
And then for the conclusion, firstly, we using review and metadata of Amazon Electronics as our target dataset to build all of these three prediction tasks. And according to the output, which expressed that all of the realistic models we built have better performance over baseline, it's really clear that TF-IDF plus linear models is simple but very effective. In addition, we also consider about some potential future works beyond our current achievement. First, a key improvement digestion is to replace TF-IDF with modern deep language models such as BERT. Well, TF-IDF can only count word frequency, but BERT learns conceptual and semantic meaning. It helps the model understand nuances like tone, product-specific sentiment, or multi-sentences reasoning. And second, apply collaborative filtering for rating prediction. Currently, our rating model predicts scores purely from review text and basic numeric features like price, but in e-commerce platforms, user item reading patterns often follow Latin structure that text alone cannot reflect. So then collaborative filtering approaches like SVD or item-based similarity can model this hidden preferences. Next slide, please. Thank you.